Good day and welcome back to the third part of our discussion on line integrals. In this video we are going to shift our attention to line integrals over vector fields, but before doing so let me remind you of our previous discussion. The starting point for any line integral is going to be a parametric description of our curve. Things that we will commonly encounter are circles or portions of, line segments, or portions of the graph of a function. And we have techniques to come up with parametric descriptions of all three of these possibilities. If it is a line integral with respect to arc length, x, or y, you in a sense just substitute in the appropriate quantities. Where in each of these cases, the starting point is exactly the same. We have a definite integral over how the parameter varies from a to b. Each x is replaced by x of t, each y is replaced by y of t. Then based upon the differential, we add on a term. So for ds, we would add on the square root of x prime squared plus y prime squared dt, a line integral with respect to arc length. With respect to x, the dx becomes x prime t dt, and with respect to y, the dy becomes y prime t dt. So based upon the differential, we see how each of these line integrals changes. In this video, we're going to shift our focus to line integrals over vector fields, which allows us to investigate a nice interpretation, something involving work. And if I was to ask you how do we calculate work, you would probably immediately tell me work is force times distance. That's a generic formula that we use. But of course there's quite a few variations of this we've seen at various points in our calculus experience. For example, in Calculus 1, we investigated the scenario where we have a variable force. That is, the force is going to change or vary as that x value or your position changes. And if you want to know the work done moving an object from A to B along the x-axis or some axes you've set up, the work is calculated as a definite integral over how you vary of the force function. Now for Calculus 3, we've been thinking more about a force vector because we have multiple directions that we can move in. And if you have a constant force that moves an object from a point P to a point Q, this is something we discussed way back in the beginning of the semester dealing with the dot product. And we said work is not quite force times distance, but if you consider the displacement vector bringing you from the point P to Q, work is force dotted with displacement. And we will take this same idea of having a variable force that we encountered in Calculus 1 and ask the similar question. What if our force is given by a force field, which means the force vector depends upon the location you are at in the plane? And if we move a particle along a curve, how much work is done by that force field? And it's worth taking a moment to just note that this force field is something in our previous section we would call a vector field. With any new topic we encounter, there's varying levels of work that we can include to demonstrate where the formulas come from. And this is one of those scenarios that since we've already set up several definite integrals, I'm going to give us a starting point, a bit of intuition, and then a finishing formula that we will use, and you can find more details in the textbook. So the work is going to be calculated as a line integral over the curve C, and we're somehow going to have to integrate something dealing with this force vector field F. And our basic approach, as it typically is with any definite integral, would be to take the curve C, break it up into a bunch of little pieces, and then on each piece what we would like to do is approximate how much work is done. So on each piece we need to think about what is force dotted with displacement. So it would be force, dot it with something representing that direction you would go and the length of it. And how we would get that direction is the unit tangent vector. And then additionally, this would be a line integral with respect to arc length to take into account the length. And if we can go with this starting point, we will now have a definite integral that would represent the amount of work that we would like to calculate. And in this case, let me note that I'm going to think of C as being a curve given by a vector-valued function r of t as t varies from A to B. Then the value of this work is going to be the definite integral over how that parameter value varies. And then we need to substitute our parametric description into that vector field, which we've represented by f. So notationally, we'll say f of r of t, and then we dot it with something. And what we'll end up dotting it with is r prime of t dt. And let me just emphasize once again, we've left out details, which you can certainly find in the textbook, and let me know if you have questions. Let's make a few more observations related to this formula. To recap what we've seen on this previous page, if we have a vector field f and a curve c that we have a parametric description of, we can define what we will now call the line integral over the vector field, which we will notationally represent as f dotted with dr, which is somewhat of an abuse of notation, but it is a standard convention, so we will go with it. And recall that this is calculating work, how much work is done by the vector field as a particle moves along this curve from the starting point at r of A to the finish point at r of B. And the formula we came up with is that we evaluate the definite integral from A to B of f evaluated at r of t, and then note the notation, dr is telling us r prime of t dt. So we once again substitute in the appropriate quantity for that differential. Now note there's some abusive notation going on here as well. When we have f of r of t, we're suggesting that we want to substitute our parametric description into the vector field. So each x becomes an x of t, each y becomes a y of t. So just to rewrite this one more time for fun, this would really be f evaluated at x of t for x, y of t for y, dot it with the vector r prime of t, which is x prime t, y prime t. And once you get it to this point, you have a dot product you can take care of, and then a definite integral, which you can evaluate. Another observation I would like to make is that we can relate a line integral over a vector field back to our previous topic. If the vector field f is made up of a first component p and a second component of q, then this quantity we are integrating is given by f dotted with dr, which we might think of as dx dy. So notationally, this is equivalent to the line integral over c, and if you evaluate that dot product, you think p dx plus q dy, which is something we will encounter multiple times, and hence you will get multiple reminders in upcoming sections. And let's now finish the video by evaluating one of these line integrals over a vector field. And I should note that the questions can be asked in many different ways. We could simply give a parametric description and a line integral and say evaluate, or we could ask you in a more roundabout way to find work, which is done. So note the reminder, and I'm going to leave some space here to include some details. The work is going to be the line integral over the vector field, which means we need a parametric description of the curve so that we can substitute in appropriately in our above formula. Our particle moves around a circle of radius 2, centered at the origin, exactly once in the counterclockwise direction. And I recommend always sketching a picture just in case it helps or gives some bit of intuition. So we go one time around the curve, which is made up of a circle of radius 2 centered at the origin. And note, because we are going in the counterclockwise direction, the parametric description of choice would be x of t is 2 cosine t, 2 being the radius, and y of t is 2 sine of t. And as that parameter value varies from 0 to 2 pi, you go precisely one time around in the counterclockwise direction. And note, if you would like to go in the clockwise direction, you can simply include a minus sign with the y of t. Now, in order to substitute things in, we need r of t and r prime of t. So r of t, a vector-valued function representing this curve, is 2 cosine t, 2 sine t. And r prime of t would be made up of the derivative of its components, so minus 2 sine, 2 cosine. And using our work above, we need to take the definite integral over how the parameter value varies, 0 to 2 pi, and what we are going to integrate is f of r of t. So each x is going to become a 2 cosine t, each y is going to become a 2 sine t. Dot it with r prime of t dt. And as usual, I recommend taking this in a very slow, methodical, step-by-step approach to make sure we are not making any silly mistakes. In terms of our vector field F, representing the force, we have x squared comma xy. And note what this is indicating for us. We're replacing each x with a 2 cosine t, and we're replacing each y with a 2 sine t. When we do that, we would have the definite integral from 0 to 2 pi. We have a vector given by x squared, so 4 cosine squared. The second entry is x times y, so 2 cosine times 2 sine. Dot it with the r prime of t above. And I would refer to this as being the new part of the problem. Evaluating this is now hopefully a reasonable exercise. If we go ahead and first compute the dot product, remember we multiply together the corresponding components and add up, we would have minus 8 cosine squared sine of t when we multiply together the first components. And when we multiply together the second components, we would have an 8 cosine squared t sine of t. And note this works out almost too good to be true in a sense. We have the integral from 0 to 2 pi of 0. And anytime you evaluate the definite integral of 0, you simply get back 0. And let's finish with a few observations. First, just in terms of presentation, your work should essentially look like this. The key ingredients would be a picture of the curve, your parametric description, a starting point, and then nice, organized, notationally correct work. In terms of this given problem, though, we might now wonder, what can we say about this 0? How do we interpret this? It's supposed to be representing work done by this force field. And in this case, I would like to make an observation without any work, is that F, the force field, is perpendicular to our curve C. And if F is perpendicular to the curve C, it does not help or hinder the motion. And if it is not helping or hindering the motion of the particle, it does no work to move the particle along that curve. And in general, we think if the vector field is helping the particle move along the curve, we should have positive work. If the vector field is hindering the motion of the particle along the curve, we would have negative work, which we'll investigate a bit more in our next video. So stay tuned and take care.